three-phase transformer connections. For a generation, we know that in the power station we have got a three-phase alternator or a synchronous generator. Then for the transmission purpose, you are using a three-phase transformer. Hence, once again, at the distribution end, once again you are stepping down the voltage from the three-phase transformer. Means for a network of a three-phase system, we need a three-phase transformer. Then three-phase transformer can be used in two different fashions. We know that one single unit of a three-phase transformer, or there is a single phase transformer, three single phase transformer. Thereby, we are connecting three single phase transformer in the different configuration. Either it may be star star, delta star, delta delta, star delta, delta star, zigzag star, VV, Scott connection. Anything you can connect in the using the single phase transformer. That is, it is meant for three phase connections. Means we have got a single unit of a three phase transformer that can be used, but we know that there are certain disadvantages of a three phase transformer because its construction is very huge and the weight is very high weight, and because of that there is a problem of the transporting and the installation. However, then compared to a single unit of a three phase transformer, we are going for a three single phase transformer for three phase transformer connections, because the another advantage is that is, if anything happens, any fault occurs on a three phase single phase transformer, three phase transformer, one unit, in that case what happens, the whole system is set. Suppose if you are using a three single phase transformer for three phase transformer connections, if anything happens to the one of the single transformer, that can be the service will continue with the other remaining two transformer, and subsequently it can be replaced. Okay, that is the advantage of a single phase transformers connected for three phase operations. The transformer connections, they are broadly divided into star star, delta delta, star delta, delta star, zigzag star, VV connection and Scott connections. And if you look into the basics of the star connection and the delta connection, that is, we have to look into the what is the relation between phase voltage and the line voltage, phase current and the line current. Then the ratio when if you are connecting for delta star or star delta. Okay, that is, first I will take up here star connections. We know that the phase voltage is line voltage by root 3. The phase voltage is line voltage divided by root 3, or in other words, the line voltage is equal to root 3 times the phase voltage. And in the case of star connection, the phase current is equal to line current. Both are same. Similarly, line current is equal to phase current. If you are taking a delta connection system, three phase system, in that case the phase voltage and the line voltage are same. Therefore, Vp is equal to Vm. Similarly, the line voltage VL is equal to Vp, Vp is equal to VL, or VL is equal to Vp. But in the case of current, if we are taking the current relation between the line and phase, in that case, the phase current is line current divided by root 3, or line current is equal to root 3 times phase current. Then we have to define the transformer ratio of delta star turns ratio, star delta turns ratio, and at the similar time we have to look into what is the voltage ratio of that one. Whatever be the connection from the primary to secondary, whether delta star, star delta, whatever be the case, but the number of turns which is involved from the primary to secondary or secondary to primary, that is what we are calling is transformer ratio. That is, secondary number of turns to the primary number of turns, what we are defining is transformer ratio. Then if you are taking the voltage ratio in terms of its the line value, that is secondary voltage. It is just the secondary voltage. Secondary voltage means here it is star connection. Means it is root 3 times the phase current. Root 3 times the phase current. That is why I am expressing here it is line voltage. It is root 3 times the phase voltage because it is star connection. Whereas in the primary, we have got a delta connection, phase voltage is equal to line voltage, that is equal to V1 only. Therefore, it is root 3 V2 by V1 is the voltage ratio, whereas N2 by N1 is the turns ratio. If you are looking to star delta, that is the secondary is connected star, the primary is connected to star. Here, the once again the turns ratio is N2 by N1. And if you are taking the voltage, the secondary voltage is delta. In the delta, we have got phase voltage is equal to line voltage, therefore only V2. Whereas in the star connection, we have got a line voltage equal to root 3 times phase voltage, therefore it is root 3 times V1. These are the basic the concept you have to understand for how you have to find out the voltage ratio, turns ratio for different configurations. First, I will take up here the star-star connection. Means I have got a 3 single-phase transformer. The primary also connected in such a way that it is act as a star, and secondary is also a star. Then, where this star-star connection is used? That is, star-star connection is generally used for small high-voltage transformers. Because of star connections, the number of required turns per phase is reduced. We know that we want for example, if you are taking the line voltage, we want 440 volts. Then we know that in the case of the star connection, the phase voltage is equal to line voltage divided by root 3, or the line voltage is equal to root 3 times phase voltage. Means the phase voltage is less, means we were considering the individual the transformer, the voltage across individual voltage across the windings is Vp. That is, Vp is the voltage in the each single phase transformer. Okay. Then if you want a line voltage, then how much you are getting from the same the Vp, how much line voltage you are getting? It is a root 3 times Vn. Means the number of conductors which is required to get large value of the line voltage, we need a smaller value of windings. The same thing is what he is telling is, because of the star connection, the number of required turns per phase is reduced, as phase voltage is star connection is 1 by root 3 times that of line voltage. Thus, because if the number of turns are less, the amount of insulation required is also reduced. The ratio of the line voltage to the primary side to the secondary side is equal to transformer ratio of the transformer, because here is also it is a root 3 times V2 divided by root 3 times V1. Root 3 get cancelled. That is nothing but N2 by N1. Means for star-star connection, the ratio of the line voltage on the primary side and the secondary side is equal to the transformation ratio of the transformer, that is N2 by N1. The line voltage on both sides, are in phase with each other. That I will show you in the vector diagram. This connection can be used only if the connected load is balanced. That is the star. One more point important point you have to remember here, that this star-star connection is used only for the balanced condition. If you are using for unbalanced condition, there is a shifting of the neutral. That is a problem with the star-star connection. That we will see later. First, how exactly this star-star connection is connected here. I have got one transformer, each its phase voltage. You can look into here. The phase voltage is 254 volts. The primary, secondary I have got 25.4. Means I am taking the ratio of 10:1. I got a second transformer and got third. Means I am having a 3 transformer. I can connect this as a star-star, star-delta, delta-delta, whatever the case. Okay. Now we are taken up here star-star connection. Therefore, what you have to do is, one common end point of all the transformer is shorted. You can see here it is all this end, the start and finish of second transformer, start and finish of the third transformer. All end point of the transformer, one winding is shorted here. It is become a star point. Therefore, we are having the phases A, B, C, and this one is neutral, which is common. It is a neutral. This is a phase A, B, and C. Similarly, secondary is also connected in star. All these, then I am having here. See here. Here my phase voltage is 250 volts, whereas line voltage is 440. However, because the phase voltage is equal to line voltage by root 3, or line voltage is equal to root 3 times phase voltage. Means we are having a 250 volt phase voltage. For that we are getting a line voltage of 440 volts if you are connected in star. If you are connected in star, that is the advantage. Therefore, the number of the conductors required are less. Therefore, the insulation required is also less for get the 440 volts by 250 volts single phase transformer each. Therefore, this is ABC. Then I am considering here the secondary is also star. Therefore, all the points are shorted here. That is the end points is shorted here. Then here you can look into here the phase voltage is 25.4. Then here it is a root 3 times 25.4, that is 44 volts you are getting. It is also 44 volts. Therefore, this is your primary, this is secondary with the ratio of 10:1. This is how you have to analyze. That is a smaller phase voltage, we are getting a larger line voltage. Therefore, the insulation required is less. The insulation is required is less. Then these are the secondary terminals A, B, and C, and the neutral. Some of the connection in the star connection. The star connection can be connected in two different ways. One is called as zero phase shift. The another one is 180 phase shift. What mean by that zero shift and the 180 shift? That we will look into things. We have got a primary winding. We have the primary winding. It is star connected. Therefore, I am drawing here A, B, and C in this way. And the secondary also have got A, B, C, the phase sequence. You can see this phase of A is same in the lines in the same plane as the primary. B has got the same plane as the primary. Then the secondary of the phase C is in plane with the primary of C. Means there is no phase displacement between the primary and the secondary. Therefore, it is called as zero phase shift connection. It is called as zero phase shift connection. Therefore, suppose if you are drawing the vector diagram for this, the first what I will draw is for the primary side. That is A. This is a voltage across the phase A. This is B, and this is C. Then in the secondary, it is zeros in the same plane you have to draw. That is A with whatever the ratio you have got. Either you can draw a smaller vector here or a bigger vector depending upon the transformation ratio. This is a B and the C. And this is what you are getting is zero phase shift. Means A and A are in phase, B and B are in phase, C and C are in a phase. Means there is no shift from the primary to the secondary. Then you have got one more connection here. It is 180 degree phase shift connection. Then how exactly it is looks like? That is, first I am drawing the primary winding as ABC. Here once again ABC I have got. Then the secondary is 180 degree phase shift. That is, first I am drawing as it is. It is A, B, and C. Now I am making 180 degree phase shift. That is, you look into here carefully. This is secondary. Now I am shifting this to 180. See, previously it is where A is. We will look into once again. Previously it is here, and here it is shifted to 180. Means from here to here it is shifting. It is exactly opposite to this. Therefore, the phase shift here in this case is 180 degree. Therefore, then how we have to drawing the vector diagram for this. First, the primary as it is, A, that is in phase with this, and B, voltage B, and it is C, here it is C. Then your A for the secondary will start here. Therefore, in phase with this, you have to draw your the vector A here. That is A in phase with B. It is a B and C. To look into compare the primary and secondary voltage of phase A. See here, it is a phase of A and it is a phase of A in the secondary. It is exactly 180 degree. Therefore, it is called 180 degree phase shift. Similarly, B also you can observe here. It is a primary side here and secondary side here. It is exactly 180. And similarly, see here, it is downwards. It is exactly opposite. That is for the secondary of the C phase. Means the shift of the from the primary to secondary voltage is here 180 degree depending upon the connection of the transformers. Okay, the same thing is explained here. If the windings terminals of secondary reverse 180 degree connection is obtained, this is what we are shown here. Then some of the other important the points regarding to star connections you are already discussed. This type of transformer is most economical for small current and high voltage transformers. Some of the advantages are the number of turns per phase and the amount of insulation is minimum because we know that the phase voltage is equal to 1 by root 3 times the line voltage. There is no phase displacement between the primary and secondary voltages. With the star point available on both sides, it is possible to provide a neutral connection. There is a possibility of connecting a neutral connection here. Some of the disadvantages of the star-star connections are listed here. If the load on the secondary side of the transformer is unbalanced, if the secondary load is unbalanced, the phase voltage of the load side changes due to load star point or earth. That is, if there is unbalance, there is a neutral point is shifting. The difficulty of shifting the neutral can be overcome by connecting the primary star point to secondary star point. Then it is avoiding, it can make use for the unbalanced condition also. Because if you are not connecting the primary and secondary, the neutral, then there is shifting of secondary neutral point. The primary of the transformer draws magnetizing current which has third and fifth harmonics. That is, the primary transformer draws a magnetizing current. Because of that, there is an introduction of the third and the fifth harmonics. If the neutral of the primary winding is not connected to neutral of the generator, third and fifth harmonics current cannot flow. Hence, the flux in the core cannot be sinusoidal wave, and therefore voltage will be distorted. If any harmonic contents are present in the waveform, it is a non-sinusoidal waveform. That is another disadvantage of the connecting the three single phase transformer in star-star connection. If the third disadvantage is that even if the neutral point of the primary is connected to neutral of the generator or earth, still it is third harmonics is present in the alternator voltage form. It will appear on secondary side. Means even though if you are not connecting the neutral of the transformer, it is not earth. However, there is the pure sinusoidal waveform, if it is not possible to generate from the alternator, that is injecting in the transformer also. These are the disadvantages of the star-star connection. In the next session we will see the delta connection and star delta.